Hi everyone! Welcome to Cram for Chem. Let's see how much chemistry we can study together. In this video, let's talk about compounds. Compounds are formed when atoms of two or more different elements are chemically bonded together. Water, H2O, is an example. We'll go over the three types of chemical bonds, which are covalent, ionic, and metallic. We'll also talk about what makes bonds strong and what polarity is. The first type of chemical bond we'll talk about is covalent bonds. Covalent bonds form when two nonmetals bond together. In covalent bonds, electrons are shared. Here's what that means. This is an oxygen atom. It has 6 valence electrons. According to the octet rule, atoms want to have a full shell of 8 valence electrons, so oxygen wants 2 more valence electrons. If there's another atom nearby, another oxygen for example, they can share these lone electrons. Each line here represents a pair of shared electrons. Shared electrons belong to both atoms, so this oxygen now has 2, 4, 6, 8 electrons, and this oxygen also has 2, 4, 6, 8 electrons. When atoms share electrons like this, they are covalently bonded. The formation of covalent bonds can be represented with a potential energy diagram that looks like this. On the x-axis, we have the internuclear distance, and on the y-axis, we have potential energy. What does the shape of this diagram mean? Let's start from the right. When internuclear distance is large, that means the atoms are far apart and the energy is near zero because the two atoms are not interacting. As the atoms get closer, there starts to be attraction. One element's protons start to attract the other element's electrons and vice versa. The energy going down means there's attraction. When we get to this lowest point, this is when the chemical bond happens. This internuclear distance is called the bond length, and this energy is called the bond energy. If the atoms get even closer together, the protons will start to repel each other and the energy shoots up. When we look at these potential energy diagrams, we want to focus on where this chemical bond happens. There are two types of covalent bonds. The first is a nonpolar covalent bond. In a nonpolar bond, there is little to no difference in electronegativity between the two bonded atoms, which means the atoms attract electrons to the same degree. This leads to an even sharing of electrons, like a tug of war where both sides are evenly matched. Nonpolar bonds are seen between atoms of the same element, such as hydrogen bonded to hydrogen or fluorine bonded to fluorine. Carbon-hydrogen bonds, which are super common in organic compounds, are also nonpolar. The second type of covalent bond is a polar covalent bond. In a polar bond, there is a difference in electronegativity. One atom attracts the electrons more, so there's an uneven sharing of electrons. The atom that's more electronegative will pull the electrons toward itself, and it will gain a partial negative charge. The other atom will have a partial positive charge. Polar bonds are represented by dipole arrows, which look like this. The arrow points to the direction that the electrons are drawn in, and you can think that the tick mark on the tail is like a positive sign, showing you which side has the partial positive charge. For covalent bonds, shorter bonds are stronger. So how do you get short, strong bonds? One way is to have small atoms. The distance between small atoms is shorter, which means that the bonds will be stronger. This can be represented by a potential energy diagram. Between these three elements, chlorine has the smallest atoms, so it has the shortest bond length and also the largest bond energy, which means it has the strongest bond. Iodine has the largest atoms, so it has the longest bond length, the smallest bond energy, and the weakest bond. The deeper the potential energy diagram goes, the stronger that chemical bond is. The other way to have strong bonds is to have high bond order. Bond order is the number of bonds between two atoms. A single bond has a bond order of 1, a double bond is 2, and a triple bond is 3. Basically, the more bonds you have between two atoms, the stronger the bond is and the shorter the bond is. Here's a potential energy diagram again. This shortest and deepest bond is a triple bond, and the longest and weakest bond is a single bond. The second type of chemical bond is an ionic bond. Ionic bonds are formed when a metal and nonmetal bond, or when a cation and anion bond. To form ionic bonds, electrons are transferred. Take sodium chloride, for example. Sodium has 1 valence electron. To get an octet, it wants to lose this electron. Chlorine has 7 valence electrons. It wants to gain 1 more electron. So, sodium gives chlorine its electron, and sodium turns into a positive cation, while chlorine turns into a negative anion. Opposite charges attract, and now these two are bonded. What you'll see in ionic compounds is a lattice structure that alternates positive and negative ions. These are some special characteristics of ionic bonds. They do not conduct electricity as solids because in this lattice structure, the ions can't move. They do conduct electricity as liquids or aqueous solutions because that's when the ions can move. A skill you'll often need for ionic compounds is writing their chemical formulas, and that's when you have to balance their charges. You have to make sure the total charge of the positive and negative ions is 0. This is a simple process. You just have to know the charges and cross down to get the subscripts. Take aluminum and oxygen, for example. Based on the periodic table, aluminum has a 3 plus charge and oxygen has a 2 minus charge. Now cross down. Give the 3 to the oxygen and the 2 to the aluminum. This is the chemical formula for the compound formed between aluminum and oxygen. The process is the same for polyatomic ions. Here's magnesium and sulfate. We take the 2's and cross them down. One additional step you should do is simplify subscripts if possible. For magnesium sulfate, I can simplify the 2's and get MgSO4. To get stronger ionic bonds, you want large charges and small ions. Let's look at magnesium oxide versus sodium fluoride. These ions are all approximately the same size, but magnesium and oxide ions have larger charges, with 2 plus and 2 minus, while sodium and fluoride ions just have 1 plus and 1 minus. Therefore, magnesium oxide has stronger bonds. If we compare sodium fluoride and sodium chloride, we'll see that they have the same charges, but fluoride is smaller than chloride, so sodium fluoride has stronger bonds. Let's go back to polarity again. Polarity is actually a spectrum that looks like this. When there's no difference in electronegativity between atoms, we say the bond is nonpolar. When there's a little difference, the bond is polar, and when there's a huge difference, the bond is ionic. How can you predict the type of chemical bond by looking at the chemical formula? The key is knowing that electronegativity increases from left to right on the periodic table. If you have atoms close together on the periodic table, especially atoms of the same element such as fluorine and fluorine, you'll have a nonpolar bond. If you have atoms that are neighbors, especially from different groups, you'll likely have a polar bond such as the one between carbon and fluorine. If you have atoms from opposite sides of the periodic table, such as lithium and fluorine, you'll have an ionic bond. The more toward the ionic side your bond is, we say that the ionic character increases. The third and last type of chemical bond is metallic bonds. Metallic bonds are formed when the substance consists of all metal atoms. Something special about metallic bonds is that they have a sea of electrons, which means that the valence electrons do not belong to any one nucleus. They are free to move throughout the entire metal. The sea of electrons is what makes metals good conductors and makes them malleable. There are 3 types of metallic substances. The first is the pure metal. The second is substitutional alloys, which is a mixture of metals with similar atomic radius. Substitutional alloys are a little less malleable than the pure metal, but more durable, and lets us adjust metals to have properties we want, such as being more rust-proof. A common example is brass, which is an alloy of copper and zinc. You can also have interstitial alloys, which is a mixture of metals with much smaller atoms, such as carbon, that fit into the spaces between metal atoms. Interstitial alloys are hard because the small atoms interfere with the movement of metal atoms. A common example is steel, which is an alloy of iron and carbon. To have strong metallic bonds, you want smaller cations, greater charge on the cations, and more delocalized electrons. If we compare aluminum and sodium, aluminum ions are smaller. Aluminum has a greater charge of 3 plus, while sodium is only 1 plus, and aluminum has 3 valence electrons instead of 1. Therefore, aluminum has stronger bonds. Thank you so much for watching this video, and stay tuned for more.